Let's talk about this graph here because last time I graphed it by hand, but I was getting some blank stares. So I just wanted to go through this thing. It's the graph of R equal to cosine of 2 theta. Okay, that's what we're graphing here. Okay. And we said, well, that's going to be like a 4-leafed rose. Last time we utilized our cool new area formula to actually compute the area of one petal of that rose. But I wanted to talk a little bit more in depth about the graphics of this thing. One thing that you can do is, I mean, technology is nice. Desmos is pretty nice. It happens to give you a lot of flexibility in terms of, what you can do. Sometimes you have to strong arm it to do what you want it to do, but most of the time it does a pretty good job. So the first thing I want to think about is what happens to this thing? What happens to this polar equation as theta goes from 0 to 45 degrees? Well, remember, this is the cosine of 2 theta, right? So 2 theta. So you're taking the cosine of twice whatever the current angle happens to be, okay? If I plug in theta equal to 0, I get a radius of 1, correct? Which is why this thing starts out at 1, 0. But then, as the angle increases to 45 degrees, the cosine of twice 45 degrees is like the cosine of 90 degrees, what's the cosine of 90 degrees? 0. So in moving from 0 to 45 degrees, the radius has shrunk from 1 down to 0. So this is the essence of what's happened here. See? So see my angle, that green line is like my angle going to 45 degrees. The radius is shrinking. That blue dot is kind of the point R comma theta. That radius is shrinking down to 0. Do you see that? Okay. Then here's something weird. Once I get beyond 45 degrees and I get into this zone right here, okay, 45 to pi over 2, the weird thing is, since I'm doubling those angles, now I'm beyond 90 degrees. Does that make sense? If I double pi over 4, that's 90 degrees. If I double pi over 2, I'm at pi, 180 degrees, yes? So I'm computing those cosine values. But cosine values for angles between pi over 2 and pi are all negative. Does that make sense? Okay. So the radii for cosine of 2 times this angle, the radii actually get flipped over into this place right here. Does that make sense? Because the radii are all negative, which is why if you increase this thing to pi over 2, okay, and you say go for it, look what happens. I end up down there. You see that? Thing goes down there. So in other words, I visit this thing first, and then suddenly I come down here, yeah, and I'm kind of moving in this general direction. Okay, that's interesting. And then if I go into this zone right here, okay, if I go into this zone right here, I'm still going to have a negative radius because I'm doubling things that are between what, like pi over 2. If I double pi over 2, I'm at pi, yes? And I'm doubling something all the way over to 3 pi over 4, but if I double 3 pi over 4, that's at 3 pi over 2 or 270 degrees. So doubling those angles between pi over 2 and 3 pi over 4 is basically, I'm computing the cosine of something between pi and 3 pi over 2, or 180 degrees and 270 degrees, which means I'm going to get flipped down to where? Down to here. Okay, the radius is still going to be negative. Okay, so that thing's going to flip down there. So that is if I increase this guy from pi over 2 to, what is it, 3 pi over 4, yes? Okay, and I play this game, watch what happens. See that? Okay, so I kind of start there, then I'm down there, then I'm over here. Okay, so this is the third thing that I visit, yes. Okay, this is the third chunk that I visit. And then you could just keep playing this game over and over and over again. Okay, for instance, if I go into this area right here, okay, think about that. So that's 3 pi over 4 to pi. If I double 3 pi over 4, that's like 3 pi over 2, yes? If I double pi, that's like 2 pi, which means I'm computing the cosine of something between 270 and 270 degrees and 360 degrees. That cosine value will be positive. Therefore, I will once again be back to a positive radius. Okay, so if I increase this up to pi, watch, you'll kind of see. It goes over to there now. So down, it's negative, negative, and then back to positive again. Do you see that? So that's kind of interesting how that works. And you can kind of see what's happening here. Okay, so there's the fourth part of it still going in this direction. Of course, you could probably guess that the fifth part of it would be like this, and then that maybe the sixth part of it would be up here, and then the seventh part would be here, and then the eighth part would probably be something like here. Yeah? Okay, let's go ahead and let this thing run its course, and we'll see what's going on here. So 2 pi, okay, and now it's going to be real cool. Look at that, 6, 7, 8. Yeah, 1, 2, 3, 4, 5, 6, 7, 8. You see that? Okay, so it's kind of interesting. The radius keeps flipping from negative to positive, which puts you on different parts of this. Okay, so the point never actually takes a sharp turn anywhere. Does that make sense? Even though these loops look like they make little sharp points at the origin, it always kind of smoothly transitions around so as to never make a sharp turn at any given moment. So that's kind of cool to watch, right? I think that's pretty cool. Yeah. So any questions on that? All right. What would happen if I tripled this thing? Let me see. What happened if let me stop doing this. What if it was 3 theta? Can you guys predict what's going to happen if it's 3 theta? How many roses am I going to have then? It's 3. How many loops do you think I'll have? You think it'll be 6? It's actually 3. Yeah? Okay. It's actually 3. And those lines don't make any sense, right? So I'm going to get rid of those. Okay, but watch how this thing travels. Let's see. Oh, I need this to be cosine of 3t, because that's what r is. This is just r cosine of theta, basically, right? This guy right here is just r. Yeah. So this is r cosine of theta, and then r sine of theta. Yes. Except I use t because Desmos is a machine. Yes. Okay. So it only seems to understand these things if I use t, the parameter t. Okay. So I put cosine of 3t. Now it looks like I'm back on this thing. You could probably predict how this is going to go after watching the other one. You see how this thing gets traced out? Yeah. It's pretty cool, right? That green line is supposed to be the current angle that you're at, and it whips back and forth through the origin as the radius becomes negative and positive, yes? You have to kind of flip over into different regions. What do you think it's going to happen if I have cosine of 4 theta? Yeah. Okay. Whoa, that's cool. Check that out. Okay, cosine of 4, cosine of 4. See this? Now, here we go. Look at that. That's pretty cool, right? Wow. You just stare at that for like 40 minutes, right? Let's do something even cooler. How about 26? Okay. And that means this needs to be 26. And that means this needs to be 26. Yeah. Oh man, look at that. That is crazy. Okay, this thing needs to slow down big time. You see that? It's pretty cool how that thing kind of goes back and forth through there. Yeah. Cool. All right, just wanted to talk about that briefly here at the beginning. I'll pause this and we'll go back in here and pick up where we left off last time. We had this formula for arc length. And remember, we had this formula for area that we came up with. Yes. That was like 1/2 r squared d theta from alpha to beta. Yeah. And that came from thinking through this picture. But then we also, we took our old arc length formula friend, and we came up with this formula right here. There was some nice cancellation that happened, you will recall. And it ended up that all that was left was just r squared and dr d theta squared underneath. We did dx d theta squared plus dy d theta squared, and we ended up with this guy as the result. This literally was dx d theta squared plus dy d theta squared. Remember, there was some nice cancellation and some nice trig identities that we were able to use, right? And we knew that x was equal to r cosine of theta, y was equal to r sine of theta, and we think of r as being an actual function of theta in the end. And we came up with this nice little formula right here. That's what we did at the end of last time. Okay, that's cool. So let's use this. All right. This is the formula for arc length. Okay, so let's use this to find the circumference of the cardioid. This is the upside down cardioid. It has the dimple of the heart sort of at the bottom of the thing. Yes. Okay. This is the upside down cardioid, if you will. Okay. Looks like this. Okay. We want the circumference of the cardioid, which basically means the arc length of this thing, correct? Okay. Well, okay. So we have r equal to this. That means we need to compute r squared. Yes? What is r squared? Well, that's like 1 plus sine theta squared, which is 1 plus 2. Oops, what in the world did I just write? It should be equals. It should be equal to 1 plus 2 sine of theta plus sine squared of theta. Okay? And what is, so r is this. We need to compute dr d theta for sure. Okay? What is dr d theta? What's dr d theta? Yeah, that's right. Which means that if I square this, dr d theta squared, which is what's going to be under the square root, yes? Okay? That's going to be equal to just cosine squared of theta. Therefore, if I take r squared and I add to it dr d theta squared, what do I get? Think about it. Look, I'm adding these two things together. Yes? I'm adding these two things together. And is there something that you see that is going to simplify? What? What will simplify? Cosine squared plus sine squared, yes, which is 1. So that adds to the other 1. And so I end up with 2 plus 2 sine of theta. Okay? So, I don't know, I'll call C the circumference of this thing, okay? The circumference all the way around this thing. Okay? What am I going to have to let my angles go between to get that entire cardioid? To kind of traverse the entire cardioid, what am I going to have to let my angles go between? All the way, 0 and 2 pi. Exactly right. Okay, so circumference is going to be the integral from 0 to 2 pi. The square root of that junk we just came up with. What can I factor out of that? I could factor out 2 from under the square root, yes. Okay, so actually I'm going to pull that out front here. There's going to be a little square root of 2 factor, and then it's going to be the square root of 1 plus sine of theta d theta. That ought to remind you of something. Does that remind you of something? I hope it reminds you of something. Does it? Does it remind you of something? What's that? We've done an integral like this recently. It was the cycloid. You remember? We had like the cycloid situation. You guys remember that? Okay. What did we do to solve that integral? Remember what we did to solve that integral? I'm trying to remind you of some chapter 8 stuff. Yeah. Okay, and what was the conjugate, Maria? Yeah, so let's multiply this by the square root of 1 minus sine theta over square root of 1 minus sine theta, all right, d theta. What do we end up with here? Well, let's write it out. So I'm going to have the square root of 2 times the integral from 0 to 2 pi, okay? What am I going to have under the square root? What am I going to have under the square root? Once I multiply this out, square root of what? Yeah. Over square root of 1 minus sine of theta. Exactly. Okay. Well. Okay, this is looking interesting. What do you think I'm going to do with 1 minus sine squared? That looks way worse than what I started with, but I promise it's not. What do you think I'm going to do with all that junk under the square root? What's that? Cosine squared? Okay. Yeah. And do you remember before we had to be careful about the square root of just canceling the square root with the square? Do you remember that? When was I allowed to cancel the square root with the square perfectly? If the thing being squared was positive. Yeah? If the thing being squared was positive. Well, cosine is positive. Cosine is positive so long as I'm to the right of the y-axis, yes? Cosine is positive for angles that are going to be to the right of the y-axis. Okay, so one thing I can do is the following. Okay, let's see if you buy this. What I'm going to do is I'm going to say, look, I could do from 0 to 2 pi, but the problem is I'm going to run into cosine values that are negative, yes? But in the end, what I can do is just take half of that cardioid, yeah? Let's kind of do the right half of that cardioid. But then since I want to have continuous angles the whole time, I don't want to like go from 270 to 360 and then jump back to 0 and go to pi over 2. That would be stupid, yes? Maybe what I should do is instead say, how about negative 90 degrees up to where? 90 degrees, yeah? Okay, and then just double the thing. That would be half the cardioid. Does that make sense? All I'm doing is trying to make sure that I have cosines that are positive, yeah? Okay, so it's going to be 2 times the square root of 2. I'm doubling it, but I'm going to change my angle measures or my limits of integration to angles where the cosine is positive. So what are my limits of integration going to be? Minus pi over 2 to pi over 2. Okay, and then I can just say that the square root of cosine squared is what? Cosine, straight up, because it's positive. Cosine of theta over the square root of 1 minus sine of theta d theta. Okay? All right, questions on that so far? Does this not remind you a lot of what we did with the cycloid? The cycloid, yes? Remember the cycloid situation? We were trying to figure out what the arc length of one arc of the cycloid was. We had a similar integral and a similar situation we were faced with there. So any questions on this so far? Questions? Okay, well, let's finish this integral, okay? what I'm going to do is I'm going to actually go into a whiteboard here and we'll finish doing this integral. Okay, so here we go. Okay, we were doing the cardioid. Yeah. And what we had was that the circumference of this thing, circumference is equal to 2 times the square root of 2. Never mind the work that we did to get to this point, but we got that the circumference of that thing is 2 times the square root of 2, negative pi over 2 to pi over 2. Cosine of theta over the square root of 1 minus sine of theta. Okay. All right, d theta. Now, what am I going to do to solve this integral? What do you guys think? This is my way of sort of trying to dig up some of the old stuff. Okay. What am I going to do to solve this integral? U sub. Okay, what am I going to put u equal to? Yeah, 1 minus sine of theta will do the job. Du is negative cosine of theta. Oops, okay, well, I can fix that by saying negative du. This is d theta. Negative du is equal to cosine of theta, d theta. Okay? Yes. Okay, so this is equal to, minus, there's a minus sign now, 2 square root of 2. The integral from, now I'm not going to write down those limits of integration because I'll change them. Okay, the integral of u to the negative 1/2 du. Yes, because it was 1 over the square root of u, basically, correct? And what are my new limits of integration? If theta is, okay, if theta is pi over 2, that's going to tell me what that limit of integration is. And if theta is positive pi over 2, it tells me what the upper limit of integration is. Okay? If theta is negative pi over 2, what's the sign of negative pi over 2? What's the sign of negative 90 degrees? Negative 1. What's 1 minus negative 1? 2. Okay? What is the sign of 90 degrees? 1. What's 1 minus 1? 0, right? I'm using this formula right here. Whatever theta is determines what u is. Okay? So, first of all, those limits of integration look backwards, don't they? Yeah? Don't they look backwards? Look backwards to me. So I could incorporate that minus sign and just get 2 square root of 2, the integral from 0 to 2 of u to the negative 1/2 du. Okay? What's the antiderivative of u to the negative 1/2? What's the antiderivative of u to the negative 1/2? 2u to the 1/2. Yeah. Okay, and that's integrated between 0 and 2, which, interestingly, is going to be 2 squared root of 2 times 2 squared root of 2. Okay? Which is like what? 8. Okay? That ought to be eerily reminiscent of what we did with the cycloid back in the day, yeah? Or a few days ago or whatever we did, yeah? Okay? So 8, interestingly, the distance around that crazy cardioid is 8. How weird, right? But the distance around that thing is exactly 8, which I think is pretty interesting. Okay? Right, this was, just to remind you, this was the graph of r equal to 1 plus sine of theta. Yeah? And if you will recall, right, so this is like 1, this is -1. This guy up here is 2. That's how high that is up there, yeah? So the distance around that thing is exactly 8, which is just sort of bizarre, okay? But it was kind of weird. Do you remember what the formula was for the cycloid? What did we end up getting? For the cycloid, it was 8 times whatever the radius of the wheel was. One arc of the cycloid was 8 times whatever the radius was for the wheel. So if we had a length 1 or a radius 1 wheel, then the length of one arc would be exactly the distance around this, this cardioid that we have here. So that's interesting. Okay. All right. Let's go back to what we were doing before. Okay, here we go. Let's talk about the area of a surface of revolution, shall we? Okay. Now remember, before we said, okay, well, you basically have this little piece of arc length right here. This guy right here basically has to do with arc length. Remember that? Yeah? There was like a tiny piece of arc length, and then it was 2 pi times the radius, yes? 2 pi times the radius of this thing. But look, if I have a curve, look, I'm gonna really just like go out on a limb here and try to draw a picture. Okay. So watch this. Suppose my curve does something like this. Okay. Okay, and so this is, this is alpha, and this guy right here is beta, those two angles. Okay. And of course, this is given by r equal to some function of theta. Okay, that's what that curve is given by. And suppose I'm at a particular angle in between alpha and beta. Okay, then what is the radius? What is the radius of, if I were to revolve this around, do you guys realize, I mean, look at this. Look, this could be very bad. So just please be kind to me, okay? This could be very bad, but look, I'm going to revolve this around the polar axis, basically. Okay. See that? I kind of revolve that thing around like this. Okay, of course, this is my radius right here, isn't it? Yeah? Oh, wait, hang on a second. That's not what I wanted to do, sorry. Let me redo this. It says, what if you revolve about the polar axis? Sorry, let me redraw this thing. Okay, revolve about the polar axis. Okay, so here's alpha, or this is beta actually. Here's alpha. Okay, and then I'm kind of looking at this curve like this. Revolve about the polar axis. What does that mean? Where's the polar axis? Which axis is the polar axis? Okay, that's this one, or that's this one down here, okay? Okay, so they're saying to revolve around this guy right here. That's the polar axis, okay? And if I do that, okay, and I revolve this thing around, I'm going to get little discs like this. Okay. And what is the radius of that thing? The radius is the y coordinate, yeah? The radius of this thing is the y coordinate. And the y coordinate is given by r times what? What's the y coordinate in polar coordinates? It's r times sine of theta. Okay, which by the way, if r is equal to f of theta, then that's going to be f of theta sine of theta. So what is this right here? This guy right here is just y. You see that? That's what y is right there. So this is 2 pi y, which by the way is just the distance around this thing. Okay, the circumference of this thing is 2 pi times the radius, which happens to be y. Yes? Okay. So 2 pi y, this guy right here is the circumference, and this guy right here is the arc length. A tiny little piece of arc length. You multiply circumference by arc length, and you're going to get the area of a little belt. Remember we talked about that before? It was like a tiny little belt. Essentially, all we're doing is just retranslating what we did over there to the case of polar coordinates. Okay? Okay. So there's that. We're kind of revolving this thing around the polar axis. We get this formula. Revolving about the line theta equal to pi over 2 means revolving around the y-axis, yes? And in that case, your radius would be the x-coordinate, not the y-coordinate. The radius would be the x-coordinate there, not the y-coordinate. Okay? Okay, any questions on that? I'm not going to try to like invert that curve down there, but you get the idea. If I revolve this thing around, I'm going to get some kind of three-dimensional surface, yes? And what we're trying to do is compute the surface area of that. Any questions on that? So we're going to do an example here to finish this thing off. Okay, find the surface area of the surface of revolution obtained from rotating r equal to 3 cosine of theta from 0 to pi over 2 about the polar axis. What's the polar axis again? What's the polar axis? The x-axis, yes? Polar axis is the x-axis. Okay? Well, first of all, what does this graph look like? I'm only going from 0 to pi over 2. Let's think about it. When theta is 0, how big is the radius? 3 times cosine of 0, yes? What's cosine of 0? 1. Right, so we're out here at 3. Okay, and then what happens to the radius as I increase to pi over 2? What's happening to the radius as I increase to 90 degrees? The radius is decreasing down to 0. So it's going to go like this. Oops. Okay, so it decreases down to 0. Okay, look, I'm just thinking about various angles here all the way, and the radius decreases all the way down to 0. Okay, in fact, r equal to 3 cosine theta is going to be a circle through the origin, just like 3 sine theta would have been a circle through the origin, but it would have been sitting on the x-axis. This thing is actually sitting on the y-axis, but I only get half of it. But where did it tell me to rotate this thing? About what? About the polar axis, yes? If I rotate this thing about the polar axis, what in the world am I going to get? Yeah, I'm going to get a sphere. Do you understand? Yeah? And if I take any given angle, okay, so I don't know, this angle right here, for instance, and I rotate that thing around, then I'm going to get a bunch of discs that look like this, yeah? And you can see that y is the radius of this thing, yes? Y is the radius of this thing. So the surface area is going to be given by, okay, to get every single disk in this thing, I would have to let theta go between where and where? Where would I have to let theta go between? 0 and pi over 2, yeah? And then the formula said it was 2 pi times the radius. Okay, let's just put y there. And then it's going to be the square root, right, times the arc length. It's going to be the square root of r squared plus dr d theta squared d theta. Okay. Well, what's dr d theta? What's dr d theta? What's the derivative of r with respect to theta? -3 sine of theta. So what is r squared plus dr d theta squared going to be? Think about it. It's going to be 3 cosine squared theta plus 3 sine squared of theta. The 3 squareds can be factored out, and you're going to have sine squared plus cosine squared, which is 1. Yeah? So what is this entire square root going to collapse down to? What's that entire square root going to collapse down to? Three. Okay? It's going to be 3. It's going to be the square root of 9, which is 3. Okay? And of course, I have y, which is r sine of theta, but r is 3 cosine theta. So this is going to be 3 sine theta cosine theta. Okay, that's what y actually is when all is said and done. So let's kind of write all this down. I'm gonna pull out this 3 out to here. So this is going to be 6 pi, the integral from 0 to pi over 2. And it's going to be 3 sine theta cos theta d theta, which, by the way, if I pull the 3 out, that's 18 pi, the integral from 0 to pi over 2 of sine theta cos theta d theta. What is the antiderivative? By the way, so this was just 3 squared, just to complete the thought there. What is the antiderivative of sine theta cos theta? What could I do to actually do that antiderivative? I'm trying to dust off the old trig integrals mindset. How would I deal with sine theta cos theta? What would we do? Put u equal to something, and what would I put u equal to? Yeah, put u equal to sine theta, and then du, of course, is cosine of theta. Yes? Perfect. So look what we end up with here. This is equal to 18 pi integral. Okay, leave the limits alone. We will fix those in a minute. But this thing is just going to be u du. What are the new limits of integration? Well, when theta is 0, what is u? When theta is 0, u is sine theta, correct? If when theta is 0, what is u? 0. When theta is pi over 2, what is u? 1. And what could be easier? Think about it. What's the antiderivative of u du? Yeah, it's just 1/2 u squared. And of course, I am evaluating this between 0 and 1. Yeah? Which is going to give me 1/2 times 18 pi, which is 9 pi. 9 pi. Now, we should have a way of checking this because, after all, don't we know the formula for the volume of this thing? Do you remember? What is the formula for the volume of a sphere? 4/3 pi r cubed. And what's the radius? What's the radius of this cube or of this sphere? What is the radius of this sphere? Or actually, hang on. No, this is not volume. What should I be doing? Oh my goodness, I just erased the whole thing. Are you kidding me? That's okay. We can go ahead and compute this anyways. What was it? The radius was how much for this thing? Right, for the surface area, it's 4 pi r squared. What was the radius for that thing? It was 3 all the way across, correct? the diameter was 3. So what's the radius? 1.5 or 3 halves, yes? So the surface area would have been 4 pi times 3 halves squared, which what does that end up being? What happens to the 4's in the end? 4 and the 2 squared cancel, and what do I get? 9 pi, same thing, yeah? So the formula works, okay, which is good because it wouldn't be a formula if it didn't, right? Okay. All right, questions on that? That's kind of neat. I didn't mean to blitz the entire thing, but you know, at least it cleaned up the screen a little bit for us. All right, any questions on that? All right, we're completely done with chapter 10. Chapter 10 is in the books.